Hello everyone. For this and the next few lectures, I will be teaching about automatic differentiation and inverse modeling for computational engineering. This lecture will be the overview of automatic differentiation, and for the next few lectures, I will be teaching about automatic differentiation and inverse modeling details. When you solve an engineering problem, gradient is a very important mathematical concept, and it is also very useful in many applications. For example, if you conduct a mathematical optimization, you want to minimize an objective function. You might want to use the gradient descent method, where you descent the state variables in the direction of your gradient. And in uncertainty quantification, you might conduct sensitivity analysis, where you also need to compute the gradient or the derivative of your function. And in machine learning, it is obvious that gradient descent method is a very important tool to find the optimal weights and biases of your neural network. And in solving nonlinear equations, you also want to use gradient to perform the so-called Newton's method or Newton-Raphson method, and that's very important in many engineering problems. However, deriving and implementing gradients are a very challenging and all-consuming process. Just think about you have a very complex function, and then you want to derive all the gradients by hand and implement that. That will consume a lot of time and energy. Automatic differentiation is a way to compute the gradients automatically to alleviate this time-consuming process. The formal definition is a set of techniques to numerically evaluate the derivative of functions specified by a computer program. However, it also has many other names, as you can see from the internet materials like AutoDiff or algorithmic differentiation or computational differentiation or backpropagation. It also bears other names. There are a lot of AD software nowadays, and people are still keeping developing new ones. For example, TensorFlow and PyTorch, they are deep learning frameworks. However, in some sense, they are automatic differentiation software. And also Adapt, which is Adapt 2 and version 1 and version 2, they are automatic differentiation tool, and also they have some array supports in C++. And you also have AutoGrad in Python, and ForwardDiff and Zygote of Julia. And this lecture will be about how to compute the gradients using automatic differentiation. For example, the forward mode and reverse mode, and also one very important technique for scientific computing, automatic differentiation for implicit solvers. So we have a lot of software, and so people also benchmark those software. For example, on the left-hand side, we benchmark, the researchers benchmark the performance of the AD software on an objective function. They evaluate the gradients of a scalar function. On the right-hand side, they evaluate the gradients of a vector function, so they get a Jacobian. And we can see here, for example, if you see the TensorFlow graph mode, this is the TensorFlow graph mode, and also the PyTorch. This is the PyTorch. The green line is the PyTorch, and also you have the TensorFlow eager mode, which is the blue line, is the red line. And you can see that for the scalar objective function, the TensorFlow performs pretty good. And this black line, I believe, is the manual icon. That means you code everything by hand. That should have the highest performance. But you can see as you increase the number of independent variables, TensorFlow actually outperform something you coded by hand. Of course, this may be due to, for example, the parallelism TensorFlow uses and other optimized strategies. Also, you have this eager mode and the graph mode discrepancy. This is because for the graph modes, it is easier to do computational graph-based optimization. For example, you can just trim your computational graph before you actually run the computational graph. And because of this, In this course, we mainly focus on TensorFlow, which is pretty high performant, and we can use that for scientific computing. So before we go deep into automatic differentiation, I want to say something about how computer programs can evaluate the gradients. The simplest one is the finite difference. Well, by definition, you can write down this formula. This is called forward difference because you take a step forward. And also you have a central difference where you take a step forward and take a step backward. And this is true if you just do Taylor expansion on fx plus h and fx minus h. And this formula, the central difference, is much more accurate than the forward difference if you just do the Taylor expansion. And they are from the definition, so this guarantees the correctness of this formulation. They are very simple and conceptually simple. However, the problem is the curse of dimensionalities. For example, if you have a function f which maps from m-dimensional to a scalar, then you need to evaluate at least m times the function evaluations. And if it is from m to Rn, then you need m times n function evaluations. As we will see later, that if you use a very smart automatic differentiation, the cost will be reduced to 0.1 function evaluations. Also, it has some huge numerical error, as we will show here. For example, we want to evaluate the derivatives of sine x at 0.1. So we write a program, and we will do forward difference. This is the forward difference, f1. And we also do central difference, this is f2, and we contrast it with the exact value, which is just the cosine. And this is the result. On the left-hand side, we have the forward difference result. We also have the arrow. On the right-hand side, we have the central difference. We also have the arrow. And there are something to observe, you should observe here. For example, if you fix the step size h, you get much better accuracy using central difference. And you also see that the arrow keeps decreasing for some h, and at some point, for example, here, the arrow stops decreasing and started increasing. And this is because of the roundoff error, because h is so small that this computation is actually very inaccurate in computer programs. And this is also the case for the central difference. And this is the phenomenon you will usually observe when you use finite difference. You should read this graph from right to left where h keeps decreasing. And as you can see, originally the arrow of the gradients keeps decreasing, and the second order, and this central difference enjoys second order convergence much faster than first order. And when you do forward difference, it decreases, but at some point, the roundoff error dominates, and then you get a lot of roundoff error for your gradients computation. Another way to do differentiation in computer programs is the symbolic differentiation. Symbolic differentiation computes exact derivatives. There is no approximation error. The idea of symbolic differentiation is that you can apply these simple rules to symbols. For example, if you want to take the gradient of a constant, then it's just a 0. Then you mark it as 0. And the derivative of x itself, this is 1. This is a table here. And also you have derivatives of the summation of two variables and derivative of the multiplication of two variables. You have all kinds of simple rules. You can apply those simple rules to the symbols. And there may not exist convenient expressions for analytical gradients of some functions. For example, you want to implement some function using a third-party library, but that function is a black box to you. So the computer cannot tell which rule to apply to that function. So you basically cannot do symbolic differentiation in this case. And this is how you do symbolic differentiation in Julia, where you use SymPy, which is actually the SymPy package in Python. And I created a two-layer neural network with the weights W and the bases B. And you can see if I do symbolic computation, the differentiation, and then I get this messy expression. And if you print it out, it will be very long expression. And this is the problem for symbolic differentiation. It can lead to very complex, redundant expressions. But one thing you need to remember is that symbolic differentiation computes the exact gradient. So there is no approximation error as the finite difference. Now let's get down to automatic differentiation. Automatic differentiation is neither finite difference nor symbolic differentiation. It works similar to symbolic differentiation. It applies those rules to applies those rules to the expressions. For example, constant it returns 0, x it returns 1. But the difference is that it recursively applies simple rules to values instead of symbols. What I mean here, for example, this is best expressed by this formula. In symbolic differentiation, V here is a symbol. It's a symbol like this, which is stored in the computer program. However, in automatic differentiation, V is a value like this. Except that these values are just computed, and it is a numerical value at this point of evaluation. So, yeah, in summary, the difference is that for symbolic differentiation, V at this point is a symbol, but for automatic differentiation, V at this point is a value, and this works for other expressions as well. So it evaluates numerically the gradients of all the function units. By function units, I mean, like, for example, x or sine x or cosine x. You already know the gradient of those very simple functions, so you can just plug in the numbers and compute the gradients. And because your program is a unit composition of functions, so it evaluates according to this simple rule, the chain rule. And automatic differentiation also computes the gradient exactly without any approximation error. It is also very efficient, as we will show later.